So my name's Paul Roberts. This is a recording of a presentation that one of my colleagues, Kier Prior-Williams, gave at our event at Vinopolis in London on the 13th of June 2013. So it's part of a larger themed day around implementing and securing a resilient network services infrastructure. Now, Kier actually did a talk specifically around resilient network services. There's another presentation which we also did from Net Clarity, which talks about the security part of the infrastructure. So if you look towards the end of this presentation, you'll find a link to the Net Clarity presentation. So if we just cover the agenda for this presentation, we're going to talk about the need for resilience. We're going to be talking about the need for DNS resilience, the challenges and solutions that people face, DHCP resilience, and the benefits of integrating your IP address management with DNS and DHCP services. And then we'll wrap up with a summary. So without core network services, such as DNS and DHCP, users are going to struggle to access the network or the internet, and in fact they'll struggle to access pretty much anything. So email's not going to work, applications aren't going to work. Things are going to start breaking pretty quickly. So users will soon be on the phone to support, unless of course it's a VoIP phone, because those will be out of action as well. But the important thing to remember is that stuff will break. DNS and DHCP is core to the function of networks today. So by implementing resilient DNS and DHCP services, we can eliminate potential downtime. So if we look at DNS resilience, you might already have a lot of DNS already. You probably have actually. So for instance, Microsoft DNS, you'll be running on your domain controllers. It'll probably be AD integrated. And it probably works more by accident than by design. That's because you configure a domain controller and automatically configure a local DNS server. Before you know it, you've got DNS servers running all over your network, all over the place. There are likely to be inconsistencies with the way these DNS servers are configured. Now those inconsistencies can be eliminated partially by using Active Directory integration, but you've still got specific configurations in the servers themselves that are not replicated via Active Directory. Now one of the issues with running DNS on Microsoft is those servers aren't dedicated to running DNS. They'll be running, as well as domain controllers, they'll be running various other services as well. They may in fact be running applications. So what you'll find is that there's be a number of security vulnerabilities published, and Microsoft will fix those in a series of monthly patches. This is normally called Patch Tuesday because it comes out on a certain Tuesday every month, these patches via Windows Update. And typically those patches will force a monthly reboot. So straight away you're having to schedule downtime and resilience for that server when it gets rebooted. And of course it could be rebooting to fix some vulnerability in the operating system or another application that's got actually nothing to do with DNS itself. Now you may also have a hybrid deployment where you've got various Linux boxes also running DNS. So you could have a mixture of Linux and Microsoft DNS servers. Now Linux runs what we call BIND, which is the Berkeley Internet Name Daemon, which is the most common DNS code, if you like, that's out there. A lot of servers on the internet use it, and it's shipped with all versions of Linux pretty much. But you have to keep it updated. There are various security vulnerabilities that have come out from BIND, so you have to keep it patched. So it's very much like the Microsoft environment. You still have to keep the software updated. Although it has to be said, the vulnerabilities don't come out as frequently as once a month, for instance. So you might have to patch maybe once every 6 months or so, or once a year, to keep BIND updated and secure. So you have to think about your patching schedule. And also if you're running a mixture of BIND and Active Directory Microsoft servers, then do you integrate them? Do they talk to each other? Do they share DNS data? Or are they run in completely separate environments? So you have to think about how they integrate. And also if you've got issues, is there a vendor that you can count on for support? So if it's Microsoft DNS, you'll probably talk to your local Microsoft Support Center or your Microsoft partner, Gold Certified Partner, whatever. But have they really got the expertise to support DNS? It's quite a niche area. Similarly with Linux, I mean, if you want DNS support, you might have to go to Red Hat. If that ties you into a certain Linux platform. Have you configured any kind of resilience on these servers? So you can use like Windows clustering or Linux clustering or virtual IP addresses, but you have to set all this up like manually. Then the actual hardware itself, you need to look at whether you've configured any kind of hard disk resilience or hardware resilience, such as RAID 1 for disk mirroring, or maybe even dual power supplies as well to give you that extra resilience. Also, are you doing any monitoring or alerting? So it'll be good to have some proactive monitoring to tell you that the DNS service is actually healthy and it's resolving, so that if there is a problem, you get alerted before it becomes a major issue, and you can troubleshoot and potentially fix that problem before it becomes serious. So there are some deployment considerations as well to take with DNS. So typically you've got internal DNS and external DNS. So for your internal DNS, you would typically configure clients to talk to 2 or more servers. So obviously if the first server goes down, there's a second server that can be contacted. And you also need to look at whether there's any kind of, whether you need local survivability. So if you've got a large branch network, to all those users at those branch offices, can they operate locally without the WAN link, or have they got like a WAN connection back to a central data center, and is that WAN link resilient? So if everybody's dependent on that WAN link in order to do their day-to-day functions, do you actually need a local DNS service at the branch itself? So you could centralize all the DNS servers and reduce the number of DNS servers out there. Now if the WAN link dies and users need to be able to work or can work with local survivability, then yes, you would probably need some kind of local DNS service to service like things like authentication requests or some application resolution or even printing. Now with external DNS, that's typically used for resolution of your internet domain names, or providing a recursive service where you actually go out and resolve DNS entries on the internet. So typically you would separate those 2 services so that it's kind of split into authoritative and recursive services. That's kind of best practice. So this is all stuff that needs to be considered when you're deploying DNS. You could run it all of this on one server, but then you open yourself up to some fairly serious security vulnerabilities, cache poisoning, all that kind of stuff. So one of the issues with having multiple DNS servers is if the first DNS server goes down, then the client can start using the second DNS server. That's not a problem. But what we tend to find is on Linux servers, it's like, for instance, servers in the data center running Linux. If that first server goes down, then Linux takes quite a while before it starts querying the second DNS server. And that can cause timeouts, application timeouts, or it can give the impression that things are running really slowly because DNS suddenly takes a long time to work. So what you can do is you can use things like VIPs, virtual IP addresses shared across multiple DNS servers, which just use normal router redundancy protocols such as CART and VRRP. What that allows you to do then is configure all your clients to use these VIPs so that if one of the servers goes down, the second server will take over that VIP, normally within a second, and then be able to take over control and respond to clients. So the benefit you get there is effectively there's no downtime. It means you can do, for instance, that patching that I was talking about earlier. You can take one server down, patch it, and there'll be another server there that will take over the responsibility for resolving entries. Now there are some considerations. VIPs tend to have to work across layer 2 networks. So that means if you're trying to run a VIP across multiple data centers, those data centers would have to be connected via layer 2 or a stretched VLAN. And you also have to consider the number of high availability pairs you're rolling out. Is it really necessary to make every single DNS server resilient? So it kind of doubles the number of boxes you end up deploying. So what we can see here, we've got an example of 3 DNS servers and 2 virtual IP addresses, which the clients are configured to talk to. So let's say that the first server fails. then that virtual IP address will automatically move over onto the second server. That second server is now hosting both VIPs. So resolution still continues as normal. Now when the first server is reinstated or repaired, the VIP will automatically move back and goes back into normal mode. Now one of the things you can do is you can add additional servers into the kind of like the VIP group to give you some additional capacity. Something else that we can also do instead of VIPs is we can use something called Anycast, which allows multiple geographically diverse DNS servers to use the same IP address. You might think, well, how does that work? Don't you get a duplicate IP address conflict? But of course, those servers are in their own separate networks. They're just advertising a common IP address, which is basically advertised out as a route, like a host route out to the internet. And then the routing topology will work out which server is actually closest in terms of like hop count and cost. So the user's query is actually routed to the nearest DNS server, and this is used quite a lot these days on the internet root servers. So if that particular server dies, then queries will get routed to the next nearest instance. So you get increased availability and reliability. You can actually lose several DNS servers and you still end up being able to provide a service. You've got improved performance because you're actually talking to your kind of closest DNS server. So if you've got DNS servers in the USA and in Europe and using Anycast, then the idea is the guys in the US will use the local US DNS server without going across the Atlantic to the European DNS servers. But of course, they still can query those European DNS servers if they want to. So you kind of get load balancing as well because you're distributing the load globally amongst all those DNS servers as part of the Anycast configuration. It also gives you resilience against denial of service attacks. So for instance, if a denial of service attack is launched in Russia, it would typically impact on the DNS servers that are nearest in terms of cost and hop count to Russia. So that might affect maybe some of the European DNS servers. Some of the ones further away probably won't get impacted because of the routing topologies routing all that DDoS traffic to a specific server. So it simplifies the client configuration as well because you have fewer IP addresses to remember. You might only have 2 or 3 IP addresses to remember instead of all the individual physical IP addresses of every single server. And as I mentioned, the DNS servers on the internet, the root servers are actually using Anycast. That's because there's actually only 13 IP addresses advertised for the internet root servers. And it was decided that that isn't really enough to provide global resilience. And the root servers have come under quite sustained attack over the years. So actually now there's several hundred root servers on the internet. And these root servers are really important because it's where they hold the top of the DNS hierarchy effectively. So if you don't know where to look for a name that you're trying to look up, you'll basically ask the root servers. So they're absolutely critical, absolutely fundamental to the way DNS works. So now there's several hundred of them, all advertised via Anycast. It's a lot harder to take them all out because you've got all the distribution of load and resilience against DDoS attack and load balancing and all the benefits I've just listed here. So one of the things you have to check is that the data is consistent across all the DNS servers as part of the Anycast cloud. So if you're doing this manually, you probably have to have scripts that copy all the zone files across, make sure they're all synchronized. Of course, you could use an automated IPAM system to do that as well. And rolling out Anycast is not trivial. You need a good relationship with the network guy, or better still, you are that network guy, because they can tend to get a little bit twitchy if you have devices on the network that aren't routers that are injecting routes and participating in routing decisions. Also, troubleshooting can be a little bit tricky because you might be sending a query to an IP address, but you don't actually know which DNS server is responding. So then you have to start looking at network tools to figure out where the packet's actually getting routed. You might be using traceroute, for instance, and then looking at the hops to see whereabouts in the network it's going. Another way of providing resilience is to use load balancing. So you can use hardware load balancers in front of a DNS server farm, and that might be something like a NetScaler or an F5 box, or I think Cisco have got out of the load balancer market now, but that might be traditionally the ACE type appliance that they had. And obviously the load balancers would distribute queries automatically amongst the DNS servers and also monitor those servers for performance to ensure that the ones that are least lightly loaded are the ones that are getting used. And also obviously if a server goes down, then that server won't get used any longer. So you might already have load balancer hardware in your network that can do this. And obviously if a server fails or you're doing maintenance, you don't suffer for any DNS outages. But something to consider is that you've got additional technology now in the data flow. So you've got like an extra box, like an extra hop, effectively in the way that you have to account for. And you also have to remember you need to make sure the data on those DNS servers is consistent, so you don't get kind of inconsistent answers depending on which server you actually query. So it can complicate troubleshooting. And there are different teams likely to be involved, so you can get a bit of finger pointing and a bit of political wrangling going on. And also if your existing load balancers are already maxed out, then you've got the expensive new kit. And I know, for instance, the F5 kit is quite expensive. Just a few other things to bear in mind. DNS security, so you've got things like keeping the software updated, both the DNS binary and the operating system. You need to manage ACLs, so that's the access control lists. So you can use ACLs to secure the DNS to ensure that only authorized users are allowed to send queries and do zone transfers and that sort of thing. But also, talking about zone transfers, you need to be aware of the data flows, so where your actual DNS data is going and who's got access to it. There's also DNSSEC to consider, which is really around making DNS secure from a kind of an authentication point of view. So it's really authenticating the DNS data with a key, a security key to guarantee that the data is valid and hasn't been tampered with. But that's quite a big undertaking to roll out DNSSEC. There's also things like DNS firewalls that you can do, which is based on this technology called response policy zones. And what this allows you to do is to use DNS as kind of like a malware firewall. And you can subscribe to services that provide lists of known dodgy sites or malware sites. So the URL, for instance, is a known dodgy site, and that would appear in these blacklists that the DNS firewall can use. So effectively what happens is if you try and access a site, the first thing you'll do is you'll do a DNS lookup for that name. That will then match an entry that's in the blacklist. The DNS firewall can then block it and redirect you to a holding page explaining why you haven't actually reached that particular site. So again, it's just another layer in the security and defense processes that you can use to protect your network. Something else to consider is a DDoS mitigation service. So especially with the amplification attacks that are occurring at the moment, then you can use a DDoS mitigation service to redirect DDoS traffic away from your network, which prevents your internet pipe from being congested. And there's various providers out there that provide that kind of service. So that was DNS. Now let's have a quick look at DHCP. Again, you might already have an existing DHCP environment running on Linux or Microsoft or both. You have to look at whether you've got any kind of resilience there. Now there is actually failover that you can do. You can do DHCP failover on Linux. In Microsoft, it's traditionally been done with split scopes, but that isn't actually failover. So the problem with split scopes is that if one of the servers dies, you'll get an IP address from one of the other DHCP server, and your IP address will change. So you actually end up losing your current sessions that you've got open, which is not good in a trading environment where you have to reconnect your application. So failover allows you to maintain that IP address. Now obviously there's many devices now dependent upon DHCP. Just obviously your standard phones and wireless clients and desktops as well, but obviously you've got things like tablets and mobile phones, and there's even things like fridges and stuff plugging into the network now using DHCP. So again, you've got to look at proactive monitoring, how you support it, and the management of DHCP, and also how you document IP allocations. So you might want to reserve IP addresses for printers or servers. You need to figure out some way of documenting those. So there are various management headaches. In a Microsoft environment, you have to use separate tools. There's kind of like this MMC console thing, and both DNS and DHCP use separate consoles. And with DHCP specifically, you have to connect to the correct server. So if you've got a large DHCP environment, many servers, you have to know which one to connect to in order to manipulate the scopes. You've got limited control over those scopes as well and who you can give access to. So once you've got access to the server, you've pretty much got access to everything on that server. Now if you're running in a Linux environment, you'll be looking at the command line and good old vi to edit your DHCP configuration from. Unless you find some third-party app like, for instance, WebAdmin might be able to do something for you. And then IP address management itself is normally done elsewhere. So for instance, in a spreadsheet. So you've got all these different ways of managing different bits of the environment. Now with a single DHCP server, you're not getting any resilience there. So obviously, if you've just got a single DHCP server and the server dies, no one can get a new IP address. Now, the important thing to remember is existing clients that have currently got a lease will carry on working fine until the lease expires. So what you need to do is figure out how long you've got to restore the configuration before the lease expires. So existing clients will carry on working. If you've got an 8-hour lease, then you've potentially got, up to 8 hours to restore the configuration. Although obviously, clients that have got their lease a few hours before it failed may expire sooner. And obviously the other thing you've got is you may have lost some or all of the actual lease information. So you might be restoring the configuration from last night's backup, but you will have lost the up-to-the-minute lease information. So you're going to be relying on the DHCP server doing conflict detection, ping checks and things like that to check that it's not allocating duplicate IP addresses. And indeed, clients will probably have to change their IP address anyway. Now with split scopes, you've got multiple independent DHCP servers. Now, it's typically known as an 80-20 split. So the main DHCP server will have 80% of the leases and the other server will have 20%. So the servers are actually independent of each other. They're not talking to each other. So you have to figure out, if you lose the server with 80% of the configuration, does the remaining one with 20% have capacity to handle all the clients? The answer is probably not. So you have to be, it'll probably keep you going for a certain amount of time just doing renewals. But eventually, for instance, let's say you have a power glitch and all your VoIP phones reboot, then they're not going to be able to get back on the network. The other problem you've got is clients will have to change their IP address and getting a lease from the other server, which is not good for a banking environment. So the way around that is to implement DHCP failover, which is a DHCP protocol level redundancy. So you've got two DHCP servers now in a relationship. Now that doesn't have to be a monogamous relationship. You can have DHCP servers with more than one partner. But the important thing to remember is that they do share a common pool of IP addresses. And they synchronize lease information. So when one server gives out a lease, it tells the other server what lease it's just given out. So should that server fail, then the other one can renew it. So as an administrator, you probably need to understand how failover works if you do lose a DHCP server. It pretty much takes care of itself, but there are occasions where you might need to do some, you just need to understand how it works really. So the benefits you get obviously is resilience. So if one server goes down, the other still provides service. So you've got no risk of duplicate IP addresses. One of the other benefits you get is load balancing. So you can actually share the load across those two servers now. And typically they'll do a 50-50 split, although you can influence that. You can also have the servers on geographically different locations and different subnets. So unlike like I was talking about earlier with the VIPs and high availability requiring layer 2 connectivity, you can do DHCP failover over layer 3. So that means you can have different data centers connected via layer 3 WAN link. And then all you do is you configure your IP helpers to talk to both of those DHCP servers. In fact, we've got an example here of two DHCP servers at different sites. And then the IP helper will basically forward DHCP packets across the WAN to both of those servers. One of those servers will issue a lease, and it will then update the other server via the failover channel. Depending on which one gave the lease, obviously determines which direction that communication goes in. Now that was one-to-one failover, but you can also do failover, star failover, or one-to-many. So this might be where you have a centralized failover server and multiple primary servers distributed in maybe in a branch or a star type of configuration. So IP address management is a process that involves documenting all your IP subnets and addresses. And it can give you a centralized view of your IP address plan, avoid service disruption by eliminating duplicate IP addresses, provide capacity planning so you can plan for future growth on your network, and you also get things like granular role-based delegation. So it means now that you can delegate parts of your IP address plan out to sub-administrators, so you don't have to do all the work. Another benefit is auditing, so you can see exactly who changed what and when, and what do they do. So IPAM, it works best when you've integrated it with DNS and DHCP. This enables you to back up all of your DNS and DHCP configuration data. It basically is all part of the IPAM database. So it makes it much easier to do backups and disaster recovery. Also, you can move away from a server-by-server management approach. So instead of manually updating individual DNS and DHCP servers, you can put them into an architecture and update the architecture instead. And the architecture will then take care of updating the servers. And that allows you to keep things consistent and eliminate mistakes. One of the main benefits, though, is of using an IPAM solution and integrating with DNS and DHCP is that you just make the change once. So you provision an IP address through IPAM, it will automatically update DNS and DHCP. So we're promoting SolidServer, which is a solution from a company called EfficientIP, which provides a fully integrated DNS, DHCP, and IP address management solution. So it provides IP address plan management. It also provides its own integrated network services, so you can run DNS, DHCP straight off the box. There are other services as well, such as NTP and TFTP that it provides. But it can also be added as a kind of an overlay solution. So it supports multi-vendor services. So for instance, you can use SolidServer to manage existing Microsoft DNS and DHCP servers, as well as like ISC bind and ISC DHCP, even the Cisco DHCP server on some routers can manage, and obviously the native SolidServer itself. Now you can do active IP address tracking and reconciliation by using an optional module called IP Locator. So IP Locator will actually query your network switches and pull back device information and allow you to see and compare the difference between what you've got in your IPAM database with what's actually out being used on the network. Now the solution is provided as an integrated appliance, so there's a zero admin database with hardened OS, built-in firewall, and that enables you to, the whole appliance model means it's much easier to do upgrades, backups, and disaster recovery. So as I was saying, we can support multi-vendor heterogeneous environments. Typically what you start off with is your centralized management platform in a data center. And what we can do is we can manage your existing DNS DHCP environment. So there's no rip and replace. So it's a very cost-effective solution to get IP address management into an environment without having to rip out all the existing services and replace them with appliances. But we can also provide dedicated appliances as well. And the final part is basically we can do real-time backups and recovery. So that centralized IPAM database can be replicated to a secondary management server, which can automatically activate if the primary server dies. So you've still got the ability to do adds, moves, and changes, which is obviously going to be quite important if your primary data center goes down. You're going to be making quite a lot of changes, I expect, to flip everything over to the DR side. So as I mentioned earlier, what we can do with SolidServer is actually start managing DNS and DHCP servers using these things called smart architectures. So smart architecture is a template. There's various different templates available, which I'll come on to in a minute. The idea is you give each role, each slot has a role in the template, and you drop the server into that role or into that slot. And then you actually manage the servers via the architecture. So the configuration is automated and kept consistent. So what the sort of architectures we've got, for instance, are we've got some DHCP architectures based around a single server, one-to-one failover, star failover, and split scope, and also DNS. We've got a single DNS server, got traditional master-slave, also got multi-master, and things like hidden master, which you might use for your authoritative external DNS. So, for instance, let's say you needed to add a new DNS domain onto all your DNS servers. In a traditional Linux environment, you'd have to go to every single DNS server and add that in manually into the named.conf file. What we can do with SolidServer is you add that zone, that DNS domain, into the smart architecture, and it automatically gets pushed out to all the DNS servers that are a member of that architecture, thus keeping things consistent. And what you can do is manage multiple architectures. So in a global environment, you might have various different environments, and you can manage them all centrally from a global IP address management database. So just to give you a quick snapshot of the GUI that SolidServer provides, it's a nice lightweight GUI. It doesn't require any Java or anything, and you can use you don't have to use the latest browser versions either. It will work with older browsers. But what you get is you've got a home page with various user-defined widgets and graphs that you see, and this is all totally customizable. For instance, we've got like a top list there, so most used DHCP ranges, customized searches, quick wizards for doing regular tasks. You can have bookmarks. That's for sort of favorite parts of your IPAM database. Got alerts. And then when you actually start managing the addresses, this is kind of like your subnet view. Basically unifying both your IPAM, DNS, and DHCP data in one screen. So here we've got the IP address name and the MAC address. We've also got user-defined metadata, which you can display. So again, this is all totally customizable, the fields that you can have here. There's a global search, which works a bit like Google. You just type in what you want to look for, whether it's a name or an IP address, and it automatically goes and finds all the occurrences of that. And as you're going through and adding entries into the database, you can configure user-defined wizards. So depending on the type of device you're adding, you can get the system to prompt you for different fields, and you can do syntax checking, validation, and even things like automatic hostname generation. I mentioned briefly IP locator earlier. This is what gives you the IP address tracking. So it's identifying IP and MAC address connections, and identifying associated switches and switch ports. So from within the IPAM database, you can see immediately which switch and port a particular device is connected to. And if you give the system rights to do it, you can even shut that particular switch port down. So let's say you have a virus outbreak, some kind of malware outbreak, your IDS or IPS system is going mad. It tells you the IP address. You can search for that IP address in the GUI, and then just right-click on it and shut the port down, and that isolates that client from the network. But even without the ability to shut down ports quickly, at least you can give the network administrator the switch and port that that device is connected to. So to summarize, we talked about the need for resilient network services, how you can deploy resilient DNS and DHCP services, and the benefits of integrating the DNS, DHCP, and IP address management solution. Thank you very much. My name is Paul Roberts, but I was presenting on behalf of Kier Prior-Williams. So if you've got any questions for Kier, you can email him at kpw@callevanetworks.com. Thanks for your time.